The third method for drawing organic molecules is called the line structure. The line structure is also called the skeletal structure or the bond line structure. And this is definitely the trickiest of the three different methods for drawing organic molecules. The line structure doesn't show any carbon atoms at all. They are implied. It also does not show hydrogen atoms that are bonded to carbon. It will show hydrogen atoms that are bonded to other atoms, like hydrogens bonded to oxygens or hydrogens bonded to nitrogens. And it also, the line structure also doesn't show carbon-hydrogen bonds. So that's a lot of stuff to leave out. What we're going to do to show you how to draw a line structure, I'm going to redraw that C5H12 example that we used for the Lewis structure and the condensed structure. And we are going to turn this Lewis structure into a line structure. Okay, so first thing that we're going to do is just start erasing. This says the line structure doesn't show carbons, it doesn't show hydrogens that are bonded to carbons or carbon-hydrogen bonds. Let's start by erasing all of the hydrogens that are bonded to carbons. All the hydrogens that are bonded to carbons, we're just going to get rid of all of those. They're still there, but we're not going to represent them. Also, it doesn't show the carbon-hydrogen bonds. So all of these bonds that were connecting the carbons to the hydrogens, we're not going to draw those either. And also, we don't show any carbon atoms. So all these C's that we're using to represent the carbon atoms, we're not going to show that either. So this is all that we're left with. These are the carbon-carbon bonds. And that's the only thing that we show in a line structure, just those guys. Now this structure here, this looks weird. It's going to be easy for us to not be able to interpret that very well just because it looks funky. And so what we do is we take these 4 line segments in the line structure, instead of drawing them back to back as a series of dashes like we have here, we're going to draw them zigzagged and then physically connect them to each other. This looks much better. Looks pretty. So this, what we just drew, is the line structure for the CH3, CH2, CH2, I'm going to run out of room. CH3, CH2, 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 CH3 molecule. Here it is. When we're looking at the line structure, we know that there is a carbon atom at the beginning and the ending of every single line segment. So there's a carbon atom right here, and there's a carbon atom right here. And here's another line segment. There's a carbon atom at the beginning and the end of every line segment, so that means there's another carbon atom here. And this is another line segment, so there's another carbon atom right there. And then last but not least, there's another carbon atom right there. So it's kind of easy to find the carbon atoms in the line structure because they're just at the beginning and the ending of all of our lines. Let's practice finding the carbon atoms in this guy right here. These are all connected, so this is like a pentagon. How many carbons Again, we're going to look at all of our line segments. There's a carbon atom at the beginning and the end of every single segment. So there's 5. Finding the hydrogens is a little bit trickier because we've erased the hydrogens and we've erased the carbon-hydrogen bonds. So to find the hydrogens, we have to remember something that you learned about Lewis structures. Each carbon has enough hydrogens to give that carbon a total of 4 bonds. You learned, when you were learning about Lewis structures, you learned about the Octet Rule. Atoms prefer to have 4 bonds, 4 single bonds around them. So carbon always follows the Octet Rule, and in our molecules, each carbon atom is going to have a total of 4 bonds around it. So when we're looking at a line structure and we're trying to figure out how many hydrogens there are, we're going to look at each carbon one at a time. Like we're going to start with this carbon right here. And we're going to ask ourselves, how many bonds can we see around this particular carbon? We can see one of the bonds, the carbon-carbon bond. Since we can only see one, that means that there are 3 bonds that we can't see. 1, 2, 3. In order for that carbon to have a total of 4 bonds, there must be 3 bonds to hydrogen. Let's keep practicing that. So next carbon over, this guy right here. How many bonds can we see? We can see that it has 1 bond, 2 bonds already drawn. It wants to have a total of 4. We can only see 2. That means it has 2 more that we can't see. Next carbon over. Here it is. This guy. Ask ourselves, how many bonds can we see? We can see 1 to the left and 1 to the right. That means there are 2 bonds that we can't see. We'll squeeze those in. Next carbon over. Ask yourself, how many bonds can I see? You can see 1 to the left, 1 to the right. It needs a total of 4. We can see 2, which means there are 2 hidden. Last carbon, ask yourself, how many bonds can I see? We can only see 1 of its bonds to the left. That means, since we can only see 1, it has 3 hidden bonds, and those hidden bonds are always to hydrogens. So let's practice that down here. How many hydrogens are in this molecule? We'll start with this carbon atom right at the top. Ask yourself, how many bonds do you see attached to that hydrogen? The carbon. You see 1 to the left, you see 1 to the right. You can see 2, but you know it has 4. If you can only see 2, that means it has 2 hidden bonds. Next guy over, you can see 2 of its bonds. That means it has 2 hidden bonds. And that's the same for all of the carbons in this molecule. For all of these carbons in this molecule, we can see 2 bonds. That means it has 2, each one has 2 hidden hydrogens. Okay, let's try this molecule. How many carbons and how many hydrogens? I want you to try to count the carbons and hydrogens in this molecule. So pause the video and see if you can figure out how many carbons and hydrogens it has. You should have found 5 carbons, 1 at the beginning and the end of every single segment, and you should have found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So now I have another question for you. The first line structure that we drew, which looked like this one right here, and the line structure that I just drew, which looks like this one right here. What is the difference between those two? Are these different? Or let's even add another one in there. Let's draw it this way. It's kind of an ugly drawing. Or let's see if we can come up with another way. Are these structures, these four structures, different, or are they the same? If you're being asked a question, are they different or are they the same? The first thing that you can always do is look at the number of carbon atoms. Just looking at carbons, we're not going to look for hydrogens. This first one, as we already know, has 5 carbons in a row. This one, 1, 2, 3, 4, 5 carbons in a row. This one, 1, 2, 3, 4, 5 carbons in a row. This one, 1, 2, 3, 4, 5 carbons in a row. Because they all have 5 carbons in a row, they aren't different. They are the same molecule, five carbons in a row, drawn 4 different ways. The angle that we draw these bonds doesn't make any difference at all when we're drawing a line structure. All that matters is that we have the correct number of line segments, the shape or the angle or even the order doesn't matter. Even though most of the time we're going to draw our line structures just left to right, nice and pretty. That's the one that makes everybody the happiest. But when we draw them going in different directions, all wacky and weird, it doesn't represent a different molecule.